Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Logix with Tony Kozaczuk, who's going to talk today about how to benchmark performance on an embedded FPGA. Tony, what are some of the factors that you have to consider when you're looking at performance in embedded FPGAs?
Some of the factors to look at when you're investigating the performance of embedded FPGA are the elements that are contributing to the delay of the embedded FPGAs.
Is it merely a throughput, or are there a lot of factors involved?
It's mainly a delay plus throughput. The delay is how fast the logic performs, and the throughput is how wide you can actually clock something. So those two factors are they're used together.
Why don't you draw this out for us?
Sure.
So what are we looking at here?
Some of the factors of embedded FPGA that contribute to the performance are the IOs, how fast the IOs are, how fast the reconfigurable building blocks or CLBs are, and also the interconnect fabric, how fast can I connect the logic blocks, as well as some of the fixed functions like DSPs, how fast do they clock.
And so a DSP is still a separate piece of this, right? It's not part of the embedded FPGA, or is it?
The DSP is part of the embedded FPGA. It is reconfigurable, but it's fixed as far as like a fixed function, but it's configurable function.
Okay, so this is sort of like an embedded DSP within an embedded FPGA.
Correct.
So what does this look like in a real embedded FPGA?
So the contributing factors of any performance is how fast you could clock something, and the max frequency of a logic is derived by the summation of all the delays through the logic plus the setup time. So 1 over the summation of the delays plus the setup time would give you the maximum frequency that any logic could run. So in an embedded FPGA, there are different elements that contribute to the delays.
So, can you give us more detail in terms of what are some of the specific areas that contribute to the delays?
So when you look at the total delays, you're really looking at a flop to flop delay. So a clock is coming to one flip-flop and arriving at another flip-flop, and the signal propagating through the fabric, through logic, and with the setup time, what is the worst case timing path. So that's what we call single stage logic. How fast is a single stage logic?
And because this FPGA is embedded, you're actually working with the RTL code here, right?
Yes, this is all part of the RTL, but the RTL is very generic. Once it's implemented in a embedded FPGA, it's actually synthesized and compiled into actual physical flip-flops and physical LUTs, and also uses interconnect fabric to connect all of those together.
So the interconnect fabric is a piece of this because you're moving electrons around in there. Another piece of this is the throughput to memory, right?
The interconnect fabric is to be able to connect one logic element to another logic element. So it's equivalent to, in ASIC world, a wire. So in an ASIC, you would have a flip-flop going through some gates to another flip-flop, and you would connect that through a wire. In an FPGA, that interconnect is actually a fabric, which is either mesh or maybe some kind of hierarchical interconnect.
The problem with wires as we get into some of the advanced nodes is they're getting very thin. Does this interconnect mesh improve the performance because of that?
Well, in the embedded FPGA, the interconnect fabric is more of an architectural than it is a physical. The physical is does impact on the speed, but more than the physical is the actual architectural. How fast can I go from one logic element to another? How can I wire or not? How can I route a signal from one place to another and have the shortest route, basically?
So how does that apply to the DSP?
Well, the DSP is very similar. You have a flip-flop through a flip-flop to get maximum frequency. In a DSP, you would go through either an adder or a multiplier. So how fast you could go within a DSP is one performance factor. The other one is if you're going from one DSP to another DSP through either an interconnect fabric or a cascade mode. For instance, in our performance benchmarking application node, we go through different scenarios and different ways you can improve performance using cascaded mode versus an interconnect, for instance.
So basically you have a lot of knobs to play with here, right?
Yes, those knobs are done either by Verilog and RTL or by the compiler that the embedded FPGA maps to the technology that it's going to.
So how does this look in the real world?
So for instance, if we take a 5-tap FIR filter, which is finite input response filter, a 5-tap FIR filter has basically 5 coefficients and some timing delays. This FIR filter actually uses multiplies and additions, and if you map that into an FPGA with DSPs that have multiply and adders as DSP elements, or MACs, for instance, the different elements that will impact the performance are either inside the DSP or between the DSP elements. So for instance, a 5-tap FIR filter uses 5 MACs or DSPs, multiply and adders. So if you take one element, for instance, we call it a DSP, it might have a flip-flop to flip-flop and a multiply. So the speed of that path is one aspect of performance. Then there is another aspect of performance. How fast can I get from one DSP to the other DSP? And you could do that in 2 ways. And that depends on the actual embedded FPGA capabilities. So in some FPGAs, it requires interconnect fabric. In other words, it has to go from the wires or the outputs of one DSP have to go through the mesh or interconnect fabric to get to the other DSP. Or in some embedded FPGAs, they could be cascaded, means that the DSPs are very close together. They don't have to go through an interconnect fabric, and that could give you a lot more higher frequency in that example.
So if you do all these things right, how much of a performance gain do you actually get?
So for a 5-tap FIR filter in a 16FFC design, for instance, you could get up to almost 400 megahertz in worst case timing and process.
And if you don't take any of this into account, what would it run at?
If you don't take any of this into account, it could run a lot slower, maybe 200 megahertz, because the interconnect is a big contributor, and pipelining is if you actually have flip-flops inside your DSPs, that also will impact how fast you can do the multiply. And usually DSPs you want to multiply one multiply per cycle, clock cycle.
Does the density, the process node, have any impact on this?
Yes, it does. And the faster, the smaller node, for instance, at 16FFC versus a 28 HPC plus could have 30% higher performance.
So how do you test this and make sure it's really going to work as you think it's going to?
Yeah, one of the things that is important when you test out RTL in an embedded FPGA is to see how fast does it work and how to write RTL that is either I/O agnostic or independent of where you place that RTL in an array. Because unlike a ASIC, which if you have RTL, you could just basically time the RTL from the input of the function to the output. But in an embedded FPGA, this is a physical array, and the IOs are physically located, so you want to write the RTL in a way that is independent of the IOs. Because if something is close, if a function is close to one input, then obviously the delay between the input and the function is going to be short. But the reverse is also true. If you place a function really far away from an I/O and it's dependent upon an I/O, then that's going to be the worst case timing path. So you're not really measuring the worst case timing or frequency of a RTL. Sometimes you are measuring the placement of that RTL in the array. So that's what you really want to decouple. You really want to know how fast the RTL works in an array, regardless of where it's placed.
Tony Kozaczuk, thanks for a great explanation of a really complex subject.
You're welcome.